So, hi everyone. First of all, thanks a lot, Anita, as always. So, my name is Tobias, and I have the honor to introduce our today's guests for our, sadly, already the last session. We are finishing with a slightly different format today. So, because we have, instead of one speaker, we have a total of 4 today who will give a joint presentation. And these incredible scientists are Mila Gizalov, Ivana Podunavac, Professor Vaza Radonic, and Professor Ivana Gajansky. They all work at the Research and Development Institute for Information Technology in Biosystems, which is more generally known as the Realsense Institute at the University of Novi Sad in Serbia. This is a very multidisciplinary institute that is developing nano materials, low-cost miniature sensors, satellite imaging, robotics, and big data analytics, and apply all of these developments to the field of agriculture, and since more recent times, also to the field of cellular agriculture. Ivana is also a GFI grantee, and today she and her wonderful team will present how to use biosensors to make the production of cultured meat smarter and more cost effective. So without further ado, we want to present you Mila Gizalov, Ivana Podunavac, Vaza Radonic, and Ivana Gajansky. I really hope that I introduced your names correctly. So enjoy.
Hello.
Hi, everybody. This is Ivana Gajansky. And Tobias, thank you for this introduction and for pronouncing our names pretty well. And we are going to be 4, but we are going to do it like sequentially, so it should work nicely. Just one small correction. So both Vasa and I are the GFI grantees because we have 2 projects, Realsense 1, which I coordinate, and Realsense 2 that Vasa coordinates. And these 2 projects are going on in parallel, basically, so we all work together. Okay, so I would like to first just give a little bit more detail on the institution itself, although Tobias gave also a great introduction about that. So it's an Institute for Information Technologies in Biosystems, or Realsense Institute, and we are part of the University of Novi Sad in Serbia. And we are a relatively young institution, but actually we've been quite successful in obtaining different projects, specifically from Horizon 2020. And our institution is organized in these different centers, 3 centers for the research, Center for Information Technologies, for Sensing Technologies, and Biosystems, and these 2 development centers for innovation, business development, and product development. And basically this structure reflects what we call Biosense vision of the agriculture of the future. So the Center for Information Technologies deals with the remote sensing and data analytics concerning these data gathered through, for example, satellite imaging. So these big data, artificial intelligence softwares, we're developing these. And we use these for yield prediction, for example. And then the Center for the Sensing Technologies deals with actual production, fabrication of the sensors. And we have the Center for Biosystem Research, which as of recently is becoming also focused on cellular agriculture. And we would like to give you a little bit more details on the project. I think Vaso now is your...
Yes.
Okay.
So the Biosense Institute is a research and development institute that's mostly focused on some research and some research-oriented projects. We apply for different projects, mostly European projects, and we have participated in number of 7 framework program and Horizon 2020 project. Next, but we will specifically proud of the Antares project that's coming from this specific teaming call that's most prestigious call in the Horizon 2020 projects, when we have the strong partnership with Wageningen University in research. Idea of this project is to invest some additional contribution in human potential and in infrastructure, and thanks to this project we'll invest more than 28 million euros in new infrastructure and human potential. So the idea is to establish some new groups and to employ some new people. So we expect that our institution will fastly grow in the following period, and mostly to double the number of the researcher. Also, we have a new building with new lab capacities. So we expect to improve our lab capacities, and especially we'll have the new laboratory for the tissue engineering. So
okay, now it's like my several slides. So yes, this tissue engineering applied for basically food production, so cellular agriculture. And here, just to list, although I'm sure everybody on the webinar is fully aware of the challenges that cellular agriculture faces, and our projects, Realsense 1 and Realsense 2, try to tackle this basically the cost challenge. So since the majority of the costs still come from the cost of media, we try to use the improved sensing technologies to optimize the basically cell proliferation stage, to enable better monitoring, and potentially also to allow for the medium recycling. In line with these challenges, I'd like to show also this mind map from the Good Food Institute that shows quite well these different issues that still need to be resolved. And as you can see, bioreactors and sensors associated to growing the cells in bioreactors are a very important part of the whole ecosystem. And to make it also more clear on what we are going to talk about, we focus for now in both projects, Realsense 1 and 2, on the cell proliferation stage. So we don't yet work on the tissue perfusion, on the tissue maturation stage. And maybe you saw on the first slide, actually there is the website, realsense.rs, where you can see more details about these two projects. But also this is the website of the Good Food Institute, where we can see about Realsense 1. It's about, as I mentioned, making the low-cost sensors for better monitoring, basically for the measurements of biomass and different nutrients and metabolites. And in the beginning, we are trying to make it as low cost as possible. So and also time efficient as possible. So we are using the lab on a chip strategy. We are basically testing our sensor prototypes in the microfluidic chips in microbioreactors, and Mila will explain later why we opted to do this. So this scale down approach is definitely very useful, and you'll see in a bit why. And I switch off at this point, so Vasa takes over.
The Realsense 2 is another project that's start this year. And idea of this project is to improve and to go from the lab chip to the custom bioreactor. So the aim of this project is to identify most efficient configuration for integration of the sensor into stereotank bioreactor. So based on that, we'll make a different model of the bioreactor sensors. etc., to find the optimal solution to place the sensor inside the bioreactors. Idea is to develop and optimize this new generation of the sensor that will be development to the Realsense Fund project to improve their technology readiness level and to integrate them in the bioreactor in order to improve the whole bio process control in the cultivated meat. So in that case, will enable media recycling and will probably reduce the cost of the cultivated meat production. So based on that, we combine different aspects, and the Mila will tell you more about the idea of both projects and some implementation and realization. Thank you.
Thank you, Vasa and Ivana. As Vasa and Ivana said, I will now continue firstly with telling you why we decided to do in microfluidic chips when we talk about development of our sensors. Firstly, as you see before, we want to develop absolutely new generation of low-cost sensors to monitor some culture parameters such as biomass concentration and some nutrients and metabolites. And we decide to use microfluidic in this propose because we know that microfluidic devices can enable us to save some time and also can save us some money of bioprocessing development, and also can enable us to have a higher degree of control over process variables through controlled fluid behavior. And microfluidic, we can conclude that it is actually something that people do when they plan to resolve some, let's say, scale-up problems. Okay. Okay, this slide actually shows what we do at the beginning. We actually fabricated our custom microbioreactors with different type of materials, such as PVC, foil, PLA, acrylic, and glass. And we did it by using a combination of some cost-effective methods. This is actually now old design of our microfluidic chip, but never mind, because this is actually the basic of its, let's say, design. Okay, every single chip have 3 main layers, and between them there are double-sided adhesive tapes. And also all fabrication steps we do in our clean room here in the Realsense, and we sterilized our chips by using isopropanol and UV light. Okay, as a model of adherent cells, we are using MRC5 fibroblasts in all of our experiments. Why? Because using of this type of cells is less demanding than using a primary culture of freshly isolated myoblasts, and also use of this type of cells is definitely the cost effective. But one day when we realize how to optimize the whole system, our sensors, all of these stuffs, we will definitely try with some more relevant cell type. Okay, at the next slide, you can see some basic steps in culturing of our cells in microbioreactors. The first step is cell culturing in flasks. After that, we trypsinize our cells and count them to see how many cells we have. And after that, we choose some working concentration, initial concentration, which will be put into our microbioreactors. After that, we put our cells into incubator, and after 2 days, they were ready for the measurements. Okay, at the next slide you can see, as I mentioned before, we try to make microbioreactors with different materials. And here you can see how cells looks like in them. The first example shows MRC5 cells in PVC foil made microchips. And you can already conclude why we can't use this material, because we got all of these black dots when we monitor our cells, and we can't see clearly our cells. Are they growing, or if we maybe have some contamination? So we decide not to use this material. After that, we try with this combination of material, PVC, PLA, and PVC, and have the same situation. But when we try with this combination of acrylic and glass to make microbioreactors, we've got good results. Our cells are growing very well in it, and also we conclude that we don't have any contaminations. We sterilize them very well, and we actually decide to use this combination of material in our future experiments. Next, please. Yeah, and at the end, I would just want to mention that for development of biomass sensors for biomass, we will use these two, let's say, methods. Big absorption measurements, because cells, both living and dead, can scatter light in different ways, particularly in near infrared range, and that's actually can give us information about biomass of our cells. On the other hand, we will use impedance measurements in radio frequency range, because we also know that viable cells can act as dipoles, and that can provide us information about their concentration and also of their biomass. That's from me for now, and now my colleague Ivana Podunavac will continue with some details about sensors and I suppose modeling. Thank you.
Thank you, Mila. Thank you, Mila. So as you could hear, we tried to make our microbioreactor with different fabrication technologies and with different materials. And here in this picture, I will show you the final chip design and final chip fabrication process. So as you can see, the substrate for the chip glass is used, and the sensor is deposited on the glass substrate. Another two layers are transparent PMM layers that are cut with laser micromachining process, and the bonded layers are double-sided adhesive tapes that are made with plotter cutter in xerographic technique. So the fabrication procedure is really fast, and the materials that we use are really low cost, and that's the aim of our developing of sensors. So I just want to mention here that we deposit SU8 resist on the sensor surface in order to avoid direct contact of cells and electrodes. So please, next slide. Now I'm going to talk about design of the impedimetric sensor. So as you can see in this picture, we have interdigital design of the impedimetric sensor. That means that it is a capacitive sensor. So while cells are growing inside the microbioreactor, they are changing the permittivity of the liquid, of the medium that they are placed in. So we can detect the change of capacitance and actually the impedance. So that's the reason why we are using this design. For the fabrication procedure, wait, please go back. For the fabrication procedure of this impedimetric sensor, we used inkjet printing, and we used silver ink for sensor. And after the printing process, the standard baking process was done, and the resist was deposited on the surface with Dr. Blade technique. Next slide, please. As Mila mentioned, we were measuring impedance. So we started with some commercially available impedance analyzers. As you can see in this picture, firstly, we used one pretty old device that didn't give us, let's say, reliable results. So we had to move on to some newer one. And here in this picture, you can see that it is biologic potentiostat or galvanostat, which was used for measurements. And I just want to say here that we were working in a range of 100 to 100 kilohertz, and that we have to be really careful when generating electric fields to set the value that will not damage the cells. So the results that we got from this device, biologic potentiostat and galvanostat, was used for miniaturization of the electronics device, actually for its calibration. So please, next slide. In this picture, you can see this electronic eval board that is actually a miniaturized version for impedometric measurements. But for this eval board, we need to have a range of values that we expect for impedance in order to find feedback resistor and calibrating resistor. And then that's the reason why we have done the measurement with biologic potentiostat and galvanostat. So now we have a, let's say, compact system that can be placed inside the incubator that you can see in this left picture. And also in this picture, there are 3 sensors for commercially available, pH for oxygen and for carbon dioxide, that are optical sensors, and they are placed inside our microbioreactors, and they are in direct contact with our cells and our medium actually, and that sensors enable real-time monitoring of that parameters. So please, next. And in our experiments, we wanted to follow the cells growth during time. So we need to make a system that will enable automatization of the measurement process. And here we developed our system with Arduino, and that enables automatic collection and processing of data. And it really makes our life easier because we don't have to, I don't know, stand up during night or measuring every hour. Arduino does it by itself. Okay, please, next slide. And so I mentioned that commercially available preset sensors. We made a special holes on the top of our chip to place the sensors in direct contact with the medium with cells. And as I mentioned, it enables real-time monitoring of these important parameters for biomass cultivation. Okay. Also, in order to make an optimal condition for cell growth, optimal temperature, optimal carbon dioxide concentration, etc., our colleague, our maker, Jovan or Don, made by himself a carbon dioxide incubator. And as you can see, it has some special holes that enable us to place the whole system inside the incubator and monitor all parameters that we want in ideal conditions. Next slide, please. And here are some more pictures of that incubator. Okay. Another important part of Realsense project is developing of sensor for nutrients. And here we are trying to develop a low-cost sensors for nutrients and metabolic waste products. And today I'm going to talk to you about sensor for glutamine that we started to work on before the Corona period, let's say. So here we were using a composite of mesoporous silica nanoparticles and enzyme glutaminase. that is immobilized on the surface of MSN. And as you can see in this picture, in this reaction with glutamine, the result of this reaction gives us ions that enable us to detect them in the impedmetric measurement. So please, next slide. And here we started with some, let's say, similar design, almost a similar design, but a smaller one. It's also an interdigital design of the sensor. In this picture, you can see a small experimental setup. We again use this portable electronics for measuring the impedance, but the substrate here was PET, okay, and the sensor is deposited with inkjet printing, and the characterization of the electrodes was done with impedmetric measurement. And here in these two graphs, you can see that during time, what is happening on the electrode surface. So we can see that with time, the impedance is decreasing, but at some point it starts to increase again. So we expected here to see some kind of platform, actually to see the saturation, let's say, where the reaction on the surface of the electrode is over, and we don't have any decrease of impedance anymore. And as you can see here, it started to increase again, but we can suppose that the reason for that was the temperature in our lab, because our drop started to evaporate. These are just initial experiments, and I just want to say here that from this slope in this graph, we can discuss about the kinetic reaction on the electrodes. One thing that is important to say is that results didn't show the sensitivity of the electrodes for different concentration of glutamine, and we could suppose that the reason for that is oxidation of silver, so we had to move on gold electrodes. So please, next slide. And we were using thermal evaporation to deposit the gold, 2 nanometers of gold on the PET substrate. And by using laser etching, we cut the interdigital design of the electrode. And here, we also had to do the sonification of the electrode to be sure. In this first picture, you can see agglomerates of mesoporous silicon nanoparticles on the electrode surface, and we had to do the sonification to be sure that only that MSN left on the electrode that is chemically bonded with gold. And you can see that the quantity of MSN is really lower than in the first picture. And after testing with glutamine, after testing with glutamine, we also can see that some MSN left on the surface of the electrode. So these results are just initial results. We started working with that. So any discussion about this is more than welcome. Thank you. Now Vasa will continue.
So the last two slides is related just to Realsense Project 2. And so idea is to use these results from microfluidic platform and to scale up to benchtop tank bioreactor. So we are going from something that's more like a laminar flow to the turbulent flow. So general idea is to make a model of our sensors, model of the bioreactor, and to use the measurements results from the sensor to make some predictable model that can help us to better understand the whole process inside the bioreactor. So partner on this project is the Brown University Harris Lab from USA. So idea is to use some basic model, starting from just the model of the cell, then model of the flow, model of the sensors, and to find the adequate place to place the sensor inside the bioreactor. That case will minimize the number of the sensor, and we will have the good selectivity and specificity of the sensor. In that manner, we'll be able to better predict the whole process that happened inside the bioreactor during the cell cultivation. Next slide, please. So based on our measurement results for the impedance sensor and this some electrochemical sensors, we are starting to make some adequate model. On left picture, you can see some model of our impedimetric sensor, and that's relatively good, agree with the measurements results. Also, we modeled some laminar flow inside the microfluidic chip, but also we modeled some bigger systems such as incubator and etc. So since this project started a couple of months ago, so that's some preliminary results about this modeling. I think that was it. That's some people involved in both projects. So you have possibility to see Ivana, Mila, another Ivana and me, but there is also a lot of people that work in cooperation with us. Some of them are material science, some are engineer, chemical, etc. I would like to thank all of them for help, and thank you for your attention. So we are open for the questions.
Hello, everyone. Thank you so much for this talk, really covering a lot of ground. So I think just to start, I'm definitely curious, how do you guys envision connecting the goals and outcomes of the first set of projects, so Realsense 1 to Realsense 2? So you showed a bit this impedance modeling from the microreactor, but how do you envision taking this information to larger scale reactors?
So I can take this just for start, and then Fad,
Okay.
so you can. So basically, the Realsense 2 is envisioned as we mentioned, as a follow-up to Realsense 1, meaning that we will be using the empirical data of the sensor measurements that we gather through Realsense 1 to feed into the mathematical models and optimize them. So basically, we make the model, and then we try with the actually measured data, and we improve it. So Vaso, if you want to add, that's basically now your part.
Yeah, the sensor that will be developed in the Realsense 1 can be easily scalable to some bigger reactor. The operation principles is relatively similar. Just we can use the data and incorporate in the model. That's the basic idea. And based on that model, we can find the optimal place for the sensor just to obtain very, very good sensitivity in that point.
So you mentioned stir tank bioreactors as the basis of the modeling. Are you guys also exploring other sorts of bioreactors that have different flow systems and regimes within them?
Yeah.
Yes.
Yeah. Actually, the very first idea for the first proposal for Realsense 1, and the reason why we have this logo also, is that we wanted to go for the rocking platform, something like a wave bioreactor, and basically that proposal was not accepted, but what GFI liked was the sensor component. So that's when we decided to focus only on this. Basically, that initial proposal was also about the new type of the whole bioreactor. But now, when we have Realsense 1 and then Realsense 2, we decided to go for the stir tank bioreactors as a first step. It doesn't have to be only this. So we are also, again, considering wave-like bioreactors, maybe also hollow fiber, bioreactors. Maybe that's even better, hollow fiber, for the integration of the impedimetric sensors, because that's an issue that we have to solve, and that is going to be part of the Realsense 2, a big part of it, how to actually integrate these impedimetric sensors into the stir tank bioreactors where you need the microcarriers for the adhesive cells. So that's a little bit, it's not necessary that all types of sensors that we develop in Realsense 1 will go into the same type of the bioreactor in Realsense 2. So we can try different ones. And also we have a collaborator on the Realsense 2, Shiok Meats, and they work, as you probably all know, on the shrimp cells, and these cells are not adherent, so they are in suspension on their own. They don't need the microcarriers. So probably for them, we can implement the impedimetric sensor in the stir tank bioreactor. But for the mammalian cells, most likely we will have to go to the rocking platform where you have less of the shear stress, so not to damage also the sensors. So we'll have to see. And Vas also mentioned this Realsense 2 project started recently, like several months ago, and then we entered this whole Corona story, and we cannot enter the labs, and it's really difficult. But the good thing is that Good Food Institute mentioned it's probable that we will get prolongation of this project. So we hope that we can actually make some more progress in the future.
Yeah, I think everyone's experiencing these struggles at
Yeah.
the moment. So I definitely hope that to see what happens there. So a quick question about these impedance measurements. Are there like functional limits to where you can use them and how you can use them? For example, is there a volume space after which the results are no longer super reliable, or are they bounded some way?
Are they bounded? What? Sorry, can you repeat?
As in, can you use these impedance measurements at every scale, like also at very large scale and high volumes, or do you start to sort of lose like accuracy of the measurement at a certain point?
That's a good question.
Yes, but the sensors measure on the let's say the micro scale. So generally they measure on some certain points. So for some larger bioreactor, we'll need probably a couple of sensors, maybe 3 to 4 or less. It depends of the size of the reactor, just to measure the concentration in the whole reactor, because due to the different flow, the cell has probably different trajectory inside the reactor, but the effective measurement will be the same. It doesn't depend on the flow or the type of the reactor, just the place where the sensor is placed inside the reactor.
And you sort of started to mention it here, but just to clarify for everyone, the impedance measurements measure biomass, right?
Yes, but we'll combine that also with some optical measurements. So based, as Mila said, that the optical system can provide you the information about number of the cells inside the bioreactor. But if you measure both impedance and optical transparency of the medium with cells, you can obtain two variables. One is the number of the cells, and another one is the viability of the cells. So.
Perfect. Now, a question for Ivana. You were speaking about glutamine. Do you have some other nutritional, or sorry, yeah, nutrient rather, targets that can use a similar
No,
system?
we were just, sorry, thank you. We were just doing with glutamine the first initial test, but now we started doing this developing of these sensors. So in the future, you know, we will try to detect another nutrient, but not for now, just glutamine.
Okay, perfect. And maybe I misheard, but earlier you were describing the three sensors that plug in. You have a pH sensor, a CO2 sensor, and another one. And you mentioned that they were all optical. Is this the case?
Yes, they are connected with optical fibers, and then the sensors are at the end of our optical fiber, and we just put them in that small holes at the top of the sensor, and they are in contact with our liquid, and they measure. Just they're commercially available.
Okay. Very cool. Cool setup. So quick question, more technical one for Mila. These glass and acrylic stacked mini bioreactors that you have, are they coated in any way?
No, they're just, you know, cleaned and sterilized with UV light and cleaned with isopropanol, and that's all there.
Yeah, this is more question for Ivana because she do this fabrication.
Okay, sorry.
Yeah.
yeah. You know, we just covered the sensor with the resist. I said that to avoid the contact between electrodes and cells, but the other parts are just, you know, cleaned, and that's all.
Yeah,
If I can just add, we did try with the coating with the fibronectin, and it wasn't much of a difference. So they were actually adhering to the the glass.
They are growing very well.
I
can say even better.
Probably.
Sorry.
I guess depending on the material that you use, the UV treatment probably also creates like some sort of ion layer. Yeah, that's very cool.
We were also kind of surprised that they like it. They adhere without even without fibronectin, for example.
Yeah.
So
I guess things are probably as because this is all done in fibroblasts, correct?
Yeah.
I wonder what sort of changes will have to happen if you switch to a different cell type that maybe isn't so happy to grow on any surface in culture conditions.
That's true. Yeah.
So another question coming. Oh, yeah, definitely. Do you plan to develop single-use sensors?
So who's going to take it?
Yeah, finally. Yeah, that's generally the idea, to develop the complete system, sensor with integrated electronics and the system for the readout to make some independent sensor that can be integrated in every bioreactor or some other system.
But the sensor itself, yes, they can be single use, and that's one way to go, and that's why we want to make them as low cost as possible. And that's probably going to be the case for these impedimetric sensors. But for the sensors for nutrients, because these MSNs, the nanoparticles are not that cheap, we have to see if we can reuse these. I hope I wasn't muted.
No, you were. You were fine. We could hear you.
Yep.
So now another question: How easy do you think it is to modularize this setup? So I mean, you could conceivably switch out different sensors if you're interested in different parameters, like new parameters other than the ones you already have sort of plugins for in these microbioreactors. What are you thinking about additional parameters you might be interested in checking out as well, and if it would be possible to maintain the same experimental setup to do those measurements?
Yes, having the whole system modular would be ideal. And there was this presentation by this other company, Ospin. They already make the modular bioreactors, and it's easy to just include new module, and that would be probably the best solution for us too. And for the other nutrients or other metabolites, or not even, we don't even have to say metabolites, so we can say just medium components. It would be ideal if we could sense like different growth factors, for example. So we now started with the very basic ones like glucose and glutamine, and for the metabolites we'll be focusing on ammonia. And basically when we figure out the actual sensor, how to detect the product of the enzymatic reaction, then it depends on the enzyme that we're going to use, which component we can actually sense. So that will be more in the chemistry part to develop these. It's not easy, definitely. And the whole idea, the whole concept of the project is pretty ambitious, and we are just really at the very beginning. But I think we're on a good way, and we have to test a lot of things. So definitely with other cell types, definitely in different bioreactor configurations, and that's why we want to go into this modeling first in the Realsense 2, and then see what makes the most sense to actually do in practice.
Yeah, definitely. I think there's a lot of value in those paired projects, and you guys seem to have very nice infrastructure at the Biosense Institute to sort of tackle these problems from the top down. So really looking forward to what comes from this work. And I'm also interested because in our last session, for those of you who joined, it was on food safety, and we were talking a little bit about sensors that you could use to detect contaminants early on, for example, with their metabolic sort of output or changes in the cells. And so I think there's a lot of room to play around here once you have this sort of platform up and running.
Yeah, actually the food safety is a topic that we work on, not only related to cellular agriculture, but actually in cellular agriculture you're kind of not expecting that much of the pathogens, hopefully. But we have some other projects for monitoring of the, for example, salmonella infections, and in water, different pathogens. So we can also tap into these methodologies and potentially use them here. For example, we have another project ongoing that is about development of biosensors, again in the microfluidic platform, but combined with the isothermal nucleic acid amplification methods. So this time in Realsense we didn't include that part, but that could be also something that can be interesting to use.
Yeah, I think definitely, because those are still, waterborne pathogens are still a huge or a potential risk.
Yeah.
Awesome, guys. I think so. We don't have any more questions coming in at this moment. So then I would like to say thank you so much again for your presentations. Really appreciate all of you taking the time to be here. And really looking forward to even more exciting data that comes from your groups.
Thank you.
Thank you.
Thank you.
And just quickly, since this is our last session, it would be great if Toby, Anita, and Alex could come back for a moment. Because I just wanted to say quickly to everyone who's joined us for the past month, or even if this is your first time, thank you so much. We really didn't know what to expect going into this, but I think it's gone really well, and it was a very nice time for us. Hope it was for you guys as well. Huge thanks to Anita and Alex, who run the Culture Meat Symposium, for giving us the infrastructure and the will to make this happen, because Toby and I are quite new to this whole conference organization business, and it was really a joy to work with everyone. So thank you so much, and thank you everyone for joining us. And I know a lot of people have asked if we have recordings available of the previous sessions, and almost all of our speakers who have had their talks recorded are willing to have them re-uploaded again. So if you were unable to join earlier, or just want to catch someone's talk again, we will be posting links to those very soon, so they'll be back online. And yeah, Toby, Anita, and Alex, if you have anything to add.
Yeah, maybe I just one or two quick things to add. So, of course, also thanks a lot to you, Freya, Anita, and Alex. but there's also a lot of more people who really made this happen. Of course, these are foremost are all of our fantastic speakers, not just the ones today, but also from the previous sessions. And then also, yeah, moreover, we have like a lot of friends at New Harvest, for example, Emily and Mira, who did most of the live tweeting and who really
Kieran as well. Thank you so much for live tweeting.
Then, oh yeah, of course. Then, of course, the Good Food Institute and Mosamid, who really just like dramatically increased our reach and helped us to build this huge community that we now have. And then, of course, every single person in this community who attended these talks and who is now in the Slack channel. And we're also, just as a little teaser, we are also now discussing different formats about how to potentially continue with chaos. So really, the best thing you could do is probably just join the Slack community if you haven't done that yet. So we will post every update there. But yeah, now I guess it's the time. So thank you all again, and see you next time, hopefully.
Cheers, everyone. Have a good rest of your days.
Cheers.
Thank you so much.
Thank you.
Thank you.
Bye-bye.
Bye-bye. Thank you. Bye-bye.
Bye.